Welcome to today's video, which covers solving linear equations. At this point, we've only seen one solution method so far, and that is equations that are separable. Now, that is a very small subset of differential equations. And so today we're going to look at linear equations and how to approach solving those. So first thing we should probably review is what is a linear differential equation. So a linear differential equation, there's two components. The first one is all coefficients are in terms of x. And then the second one is that y, which is our dependent variable, and all of its derivatives are to the first power. So that was one of the very first things we learned in the first video was how to classify equations. So we're going to be focusing on linear ones today. And so if we want to write out the general form of a linear equation, we have an of x, nth derivative of y with respect to x, a of n minus 1 of x, the n minus 1 derivative of y with respect to x, all the way down to a1 of x dy dx plus a0 of x times y equals g of x. Okay, so we are going to consider the case where n is 1, which is this equation that we have right here. What we often do is we want a lead coefficient of 1, so often we'll divide by that a1 of x. And so what that gives us then is dy dx plus a0 of x over a1 of x looks just a little bit unfriendly, so we're just going to give that a different name. That's just a function in terms of x. Same thing on the right side. G of x over a1 of x, that's just a function in terms of x. So we're going to set that equal or call that f of x. This is called standard form of a linear equation. Okay, so we have two assumptions, which you can see. We are going to assume first that a solution does in fact exist. And then we are going to be looking at an interval in which p of x and f of x are continuous. So let's look at how to solve this equation. So we're going to want to multiply our differential equation by a term that we're going to find that is mu of x. The reason that we're going to do that is the left-hand side of the equation will be the derivative of the product of mu of x and y. Okay, so let's see what that looks like. If we take the derivative of mu of x multiplied by y, using the product rule, it would give us mu of x dy dx, add the derivative of mu with respect to x times y. So the question is, how is that helpful? Well, if we go back to our equation, the standard form, we had dy dx, add p of x times y is equal to f of x. If I were to multiply this side of the equation by mu, I would get mu of x dy dx, add mu of x times p of x multiplied by y. Okay, so what we said above is that we want the left side of the equation to be the derivative of this product. So we need the left side of our equation to be equal to the derivative of the product. Okay, so if we set those equal, just for simplicity's sake, from now on, instead of writing mu of x, I'm going to write mu just to make things a little quicker. So we get mu dy dx, add d mu dx times y is equal to mu dy dx, add mu times p of x times y. Okay, so these terms are already equal, which means we need these two to be equal. Okay, so if we divide y out, what we end up with then is d mu dx is equal to mu times p. Now, keeping in mind that mu is a function of x and p is also a function of x. So is this helpful? Well, hopefully you noticed, yeah, this is now a separable equation. Okay, so where do we go from there? Well, of course, we're going to separate. We get d mu divided by mu is equal to p dx, and we integrate. So we're going to get the natural log of mu is equal to the integral of p of x dx, add some constant. So then if we solve for mu, our mu is c2 e to the integral of p of x dx. So remember, we've done this before. E to the c1 gives us a constant, which I'm going to just make c2. Okay, so if we make c2 equal to 1, that gives us that mu of x is equal to e to the integral of p of x dx. Okay, so this term right here is called the integrating factor. So now that we have our integrating factor, let's see what it actually does to our equation. So remember, we said that we're going to multiply the equation by mu. So when we multiply our initial equation by mu, we get mu of x dy dx, add mu of x p of x times y is equal to mu of x times f of x. Okay, well, that mu of x we're going to replace with our integrating factor from the bottom that we found. So this is e, the integral of p of x dx, times dy dx, add e, the integral of p of x dx, times p of x times y, equals, not mu, equals e, the integral of p of x dx, times f of x. Sorry, I didn't give us a ton of room. Hopefully you found enough. Okay, so on this left side, what we wanted was the product times y. We wanted the derivative of that. And so verify that what we did in fact get, this sum, is the derivative of the product of e of x, e to this quantity times y. So that is in fact what we got. And that then is equal to e to the integral of p of x dx times f of x. Okay, so then on this left side, this integrating factor, that's really mu of x times y, is equal to e to the integral of p of x dx times f of x. Okay, of course then, at this point, we're going to integrate, which gives us mu of x multiplied by y is equal to the integral of e to the integral of p of x dx times f of x dx, all add c. Then we're going to solve for y. Okay, next page. I know that was a lot. We're going to write down what we actually just did. So if you need a minute, pause the video and look back through the steps to make sure you understand how we got from one step to the next. Okay, so here's the recap of what we just did. The first thing you're going to do is write the equation in standard form. What that means is you have a lead coefficient of 1. That's it. That's what that means. Then you're going to find your integrating factor, that mu of x. Then you will multiply both sides of the equation by mu of x. If you do everything right, the left side of the equation should be the derivative of their product. So it should be the derivative of the product of e to the integral of p of x dx times y, or mu of x times y. And then you're going to integrate. So let's see an example. Example number 1, solve this equation. So what should be going through your head right now is, first of all, is it linear? Okay, well, coefficients are in terms of x. I have a coefficient here. My coefficient here is just 1, and then I have a function of x. And then y and all of its derivatives are to the first power. Now, could we solve this by separation? is there a way for us to get x on one side and y on the other side, and then split up the dy dx? And you should be saying no. So if we couldn't solve this by separation, we're going to have to treat this as the linear equation that it is. So first thing, as we see above, is put it in standard form. So we get dy dx, subtract 1 over x times y is equal to x to the third. So that was the first step. Second step is find the integrating factor. So mu of x is going to be e to the integral of p of x dx, which in this case is e to the integral of negative 1 over x dx, which is e to the negative natural log of x, which is 1 over x. So then we're going to multiply the entire equation that we got in step 1 by 1 over x. So we get 1 over x dy dx, subtract 1 over x squared times y is equal to x squared. And then verify, left side of the equation should be the derivative of the product of 1 over x and y. And so look and make sure, is it? So what I mean is this information equal to this one? Don't just assume that it is. It should be, but if it's not, then you made a mistake. Now, ours, of course, is. So last thing that we're going to do is we're going to integrate. So if I integrate, I'm going to get 1 over x multiplied by y is equal to 1/3 x cubed plus c. In this case, solve for y if you can. If you can't get an explicit solution, which we can. So we're going to get 1/3 x to the 4th add cx. Okay, that was the first example. The rest of this video is just more examples with trickier integration. So let's take a look at the next one. Solve example number 2. So again, what you should be asking yourself, can I solve this by separation? No, there's no way for us to get the x's and dx on one side and the y's and dy on the other side. So then you're going to ask yourself, is this linear? Well, I have coefficients in terms of x, and then y and all of its derivatives are to the first power. So yes, it is linear. So let's put it in standard form. When we do that, we're going to get y prime add tangent of x times y is equal to 5x divided by cosine of x. Next thing that we're going to have to do is find our integrating factor. So it's going to be e to the integral of p of x dx, which in this case is e to the integral of tangent of x dx. Okay, so this is where the trickier part comes in. Do we remember how to integrate tangent of x? Maybe you have this memorized. I don't personally, but maybe you do. So instead, we're going to look at this as the integral of sine of x over cosine of x dx. At this point, maybe your brain is going off, we're going to have to do a u substitution. So our u in this case is cosine of x. Our du then is negative sine of x dx. So when we integrate, we're going to get negative natural log of cosine of x, which is the same as natural log of secant of x. Okay, so going back to our equation then, this becomes e to the natural log of secant of x, which is just secant of x. Okay, so now multiplying by secant of x, we get 1 over cosine of x dy dx, add sine of x over cosine squared of x times y is equal to 5x over cosine squared of x. Okay, on the left side, this should be the derivative of the product of 1 over cosine of x and y. And then on the right side, we're left with 5x over cosine squared of x. So now we're going to integrate. On the left side, we get 1 over cosine of x multiplied by y. On the right side, this again is going to involve a little bit of some side work. In this case, I'm going to use tabular. So if you remember, with tabular, you differentiate one side and you integrate the other side. You want to differentiate the term that's eventually going to get to 0. So we have 5x, 5, and 0. 1 over cosine squared is secant squared. Integrating secant squared, we get tangent of x. Oh, and how convenient. We already know tangent of x we can write as negative natural log of cosine of x or secant of x, either one. Okay, so going back to our equation then. Oh, forgot this way. So remember, positive, negative. So we're going to get 5x tangent of x, add 5 natural log of cosine of x, add c. Lastly, multiplying by that cosine of x, we get our solution to be 5x sine of x, add 5 cosine of x, natural log of cosine of x, add c multiplied by cosine of x. Okay, we've got 2 more examples, so let's take a look at the next page. Okay, so for this example 3, this is an initial value problem you'll see because we have this initial condition. Go through your mental check. Is this separable? No, it's not. Is it linear? Well, that one's not quite as obvious. It looks like we've got a lot going on, so it might be helpful in this case to write this in standard form. Okay, so what I'm going to do then is I'm going to divide everything by x and d of x. And so that will give me then dy dx plus xy add 2y subtract 2e to the negative x over x is equal to 0. Okay, so then taking a look at that second term, I have some stuff with y, which will need to stay on the left side of the equation. And then this term that is just a function of x is going to go to our right side. So cleaning things up a little bit, we get dy dx plus, I factor a y out of this right here. And when I do, I get 1 add 2 over x. And then the other term that is a function of x, I move that over and I get 2e to the negative x over x. Now we can see, yes, this is a linear equation. Okay, so let's find our integrating factor. So this is going to be e to the integral of 1 add 2 over x dx, which will give us e to the x add 2 natural log of x, which simplifies to x squared e to the x. So when we multiply the entire equation that I just starred by that integrating factor, our left side we know is going to be x squared e to the x multiplied by y, the derivative of that product. And on the right side, we're going to get 2x. Okay, so integrating then, we get x squared e to the x multiplied by y is equal to x squared at c. Can we solve for y? Yes, of course we can. When we do, we get y equals e to the negative x, and then c divided by x squared e to the x. Okay, so now going to that initial condition, y of 1 equals 0, we're going to get 0 equals e to the negative first, add c over e to the first, which gives us c equals negative 1. So our solution then is y equals e to the negative x, subtract 1 over x squared e to the x. Now, one thing that I want to talk about is oftentimes when we get these solutions, we're going to look at what happens as x goes to infinity. Well, both terms have an e to the negative x. So as x goes to infinity, e to the negative x is going to go to 0. Which means both of these terms are what we call transient terms. Any terms that go to 0 are called transient terms. So in your homework, if you're asked which terms are transient, now you know. Okay, we have one more example and then we have a quick note and we will be done. So the last example is a piecewise function. Piecewise also having an initial condition. So what we're going to have to do is we're going to actually have to solve this equation on both of those intervals. So the first thing is we are going to solve on the intervals 0 to 1. So writing our equation then, we get dy dx, add y is equal to 1. So our integrating factor then is going to be e to the integral of 1 dx, which is just e to the x. So when we multiply both sides by e to the x, left side is going to be the derivative of the product of e to the x times y. Right side will just be e to the x. So integrate, we get e to the x multiplied by y is equal to e to the x plus c. So our y then ends up being 1 add c1 e to the negative x. So this is really c1. I'm going to mark it as c1 because when we solve on this other interval, you should notice you're going to end up with another c. So then we have that initial condition of y of 0 equals 0. So if we use that, we get 0 equals 1 add c1 e to the 0. So our c1 equals negative 1. Our solution then ends up being 1 subtract e to the negative x. Now, remember, of course, though, we still have to solve on the other interval. So on the interval 1 to infinity. So if we do that, we end up with an f of x of 0. So that gives us dy dx, add y is equal to 0. Same integrating factor. So we still have e to the x times y. Then when we integrate, we're going to get e to the x times y is equal to c2. So our y then is c2 e to the negative x. Now, one thing to note here is that we cannot use the initial condition. Why not? Well, our initial condition is one where x is 0. That does not apply in this second portion of the function. So we actually can't find this c. So our solution in this case shouldn't be a shock, it's going to be a piecewise. We get 1 subtract e to the negative x when x is between 0 and 1. And then we get c2 e to the negative x when x is greater than 1. Now, for that first portion, this e to the negative x is still called the transient term. So even though that's in the part of the function where x is only between 0 and 1, x is not actually going to infinity, it's still called the transient term. Now, is there a way for us to find c2? Well, we could find c2 if we wanted y to be continuous. So we can find c2 if we want y to be continuous. And specifically, of course, we're concerned at x equals 1. Okay, so if we substitute in x equals 1, we're going to get 1 subtract e to the negative first is equal to c2 e to the negative first. So we get 1 subtract e to the negative first over e to the negative first is equal to c2. So simplifying that, we get c2 to be e subtract 1. So then if continuous, that second portion would end up being e subtract 1 e to the negative x. But again, that's specifically if we want our y to be continuous. Okay, last thing is not an example, but a quick note on the next page. Okay, is this function right here, dy dx equals 1 over x add y squared, linear? Well, currently you should say no. So currently it's not separable, it's not linear. Is there a way for us to make it linear? Well, what if we considered the equation dx dy is equal to x add y squared? Is that linear? Well, yes, this is linear with a dependent variable x. right? We could write dx dy, subtract x is equal to y squared. So this is linear. So then when we found our integrating factor, it would be in terms of y instead. So we would have e to the integral of -1 dy. So that would give us e to the negative y. So the left side then would be the derivative of the product of e of the negative y multiplied by x. And on the right side, we would have e to the negative y, y squared, and so on and so forth. So that's just a different way to look at it. So it's possible that your equation is linear in dx dy, but not dy dx. Okay, thank you for sticking with me. You now know 2 ways to solve equations: separation and linear equations. Next video, we're going to learn another one. So until next time, thank you for watching.